Physical chemistry in action. Today, we will fit autocatalytic Prout Tompkins kinetics to a differential scanning calorimetry exotherm, and then compute the extent of reaction versus time profile. We'll go step by step. Chemistry, the DSC signal, the kinetic model, parameter fitting, and finally the conversion curve. First, the DSC signal. On the horizontal axis, we show temperature in Kelvin, and on the vertical axis, we show heat flow, watts per gram. The red curve is a measured exotherm after baseline correction. Its area is proportional to the total reaction enthalpy. The baseline is the zero line. The shaded area is the total heat released, delta H total. The conversion alpha at any time is the cumulative heat released divided by the total heat. That is alpha of T equals 1 over delta H total times the integral of Q of T dt. Now, the kinetic model. The Prout-Tompkins autocatalytic model says d alpha by dt equals K of T times alpha to the m times 1 minus alpha to the n. The rate constant follows Arrhenius, K of T equals a times e to the minus e over RT. Under a constant heating rate beta, temperature equals T naught plus beta times T. Then d alpha by d capital T equals a over beta times e to the minus e over RT times alpha to the m times 1 minus alpha to the n. Our goal is to choose parameters a, e, m, and n so that the model-generated heat flow matches the DSC curve. Let's visualize the fitting. Here again is the DSC exotherm in red. The orange curve shows a poor initial guess. It misses both position and width. The green curve reflects a fitted set of parameters, capturing peak temperature and shape. We compare quality using the sum of squared errors. Notice how much the SSE decreases. Here is a parameter summary. We display the initial guess and the fitted values. Changes in A and E shift the peak position, while M and N control the skew and width of the exotherm. Now compute the extent of reaction versus time. On the horizontal axis, we plot time in seconds. On the vertical axis, we plot conversion alpha from 0 to 1. The green curve is alpha from the fitted kinetic model. The blue curve is alpha obtained by integrating the DSC heat flow, that is, 1 over delta H total times the cumulative heat. These two independent paths should agree closely when the model is appropriate and the DSC data are properly corrected. A quick statistical check. Residuals are data minus model. If the model captures the signal, residuals should be structureless noise. We summarize error with the root mean square error. The square root of SSE divided by n, smaller is better. Summary. We used DSC heat flow to quantify total enthalpy and conversion. We fit an autocatalytic Prout-Tompkins model, optimizing AEM and N. The fitted model reproduces the exotherm and the alpha of T curve, while the residuals appear structureless. This workflow links experiment, kinetics, and statistics into a clear, quantitative picture of reactivity.